The solar system you learned in school ends at Neptune, maybe Pluto. A tidy ring of planets, neatly labelled, with a vague arrow pointing outward that says, the rest of space. But the real solar system is nothing like that diagram. Beyond the planets, beyond the Kuiper Belt, beyond anything we have ever photographed, there may be a structure so enormous that the entire planetary region becomes a pinpoint at its center. The Oort Cloud. A ghostly reservoir of trillions of frozen objects that scientists believe begins thousands of times farther from the Sun than Earth and stretches so far outward that it reaches a significant fraction of the distance to the nearest star. By the end of tonight, the solar system you thought you knew will feel like a room you have only ever seen from one corner. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Are you comfortable? Now, let's begin. You already know the solar system. You have known it since you were a child. Maybe you learned it from a poster on a classroom wall, the kind with the sun on the left, bright and yellow, and the planets arranged in a line stretching to the right, each one smaller and colder and farther away as your eye moved across the page. Maybe you built one of those styrofoam models where you painted Jupiter orange and gave Saturn a ring made out of cardboard and hung the whole thing from the ceiling by fishing line. Or maybe you just absorbed it from television, from documentaries, from conversations, from the general cultural knowledge that every person carries without really thinking about where it came from. The picture is always the same. The sun in the center. Mercury first, small and scorched. Venus next, shrouded in clouds. Earth, blue and green, the one that matters to us. Mars, red and dusty. Then the asteroid belt, a band of rocky debris. Then the giants. Jupiter, enormous and banded. Saturn, elegant with its rings. Uranus, tilted on its side. Neptune, blue and distant and cold. And then, depending on when you went to school, either Pluto sitting loyally at the end, or a vague sense that the diagram just stops, that there is nothing more to show. You could probably still name most of them in order right now without looking anything up. That is how deeply the picture sits in your mind. It is one of the first pieces of scientific knowledge most people absorb, and it stays with them permanently. The solar system is a set of planets. They orbit the sun, and somewhere out past the last one, space begins. That is the map. That picture is not wrong. Those planets are real. Their orbits are real. The order is correct. The relationships between them are accurate enough to navigate by. Spacecraft have been sent to every one of those worlds using exactly that understanding of the solar system's layout, and they arrived precisely where they were supposed to. The textbook picture works. But it works the way a street map of Manhattan works if you're trying to understand the size of the United States. It is correct about the part it shows. It is just catastrophically silent about everything it leaves out. The solar system you learned does not end at Neptune. It does not end at Pluto. It does not end anywhere near where you think it does. And understanding why requires starting with the planets and then watching, step by step, as the boundary you believed in dissolves into something much stranger and far, far larger. Neptune, the outermost planet, orbits the sun at an average distance of about 30 astronomical units. 1 astronomical unit is the distance from the Earth to the sun, roughly 93 million miles, or about 150 million kilometers. So Neptune is 30 times that distance. If you could somehow drive a car to the sun at highway speed, it would take you roughly 170 years. Neptune is 30 times farther than that, roughly 5,000 years of highway driving. It took the Voyager 2 spacecraft, traveling at tens of thousands of miles per hour, 12 years to reach Neptune after its launch in 1977. Neptune is genuinely far by any human standards. The light that leaves the sun takes about 4 hours to reach Neptune. A radio signal sent from Earth, traveling at the speed of light, takes over 4 hours to arrive. When Voyager 2 was sending photographs of Neptune back to Earth in 1989, mission controllers had to wait more than 4 hours for each image to cross the distance. Neptune receives roughly 900 times less sunlight than Earth does. At noon on Neptune, if you could stand on its surface, the sun would not look like the blazing disk you see from your backyard. It would look like an extremely bright star, a point of light fierce enough to notice, but nothing like the overwhelming presence it is from Earth. And yet, in the context of what we are about to discuss, Neptune is close. Remarkably, almost absurdly close to the Sun. Beyond Neptune, there is Pluto. Pluto orbits at an average distance of about 39 astronomical units, though its orbit is eccentric enough that it swings as close as 29 astronomical units, and as far as 49. For decades, Pluto was considered the 9th planet and the outermost object in the solar system. The final stop, the boundary marker. After Pluto, the map was blank. And for most of the 20th century, that blankness felt like an answer. There simply was nothing else to find. That changed in 1992. In August of that year, astronomers David Jewitt and Jane Liu discovered an object designated 1992 QB1, a small icy body orbiting beyond Neptune. It was not Pluto. It was something else, something new, sitting in the darkness past the last known planet. Within a few years, more discoveries followed. Dozens of them, then hundreds. A whole population of frozen worlds began to emerge from the shadows beyond Neptune. Most of them small, some of them surprisingly large, all of them composed primarily of ice and rock. This population became known as the Kuiper Belt, named after Dutch-American astronomer Gerard Kuiper, who had speculated about the existence of such a region in 1951. The Kuiper Belt extends from roughly the orbit of Neptune, about 30 astronomical units, to approximately 50 astronomical units from the Sun. It is a broad, relatively flat band of icy objects orbiting in roughly the same plane as the planets. It contains an estimated hundreds of thousands of objects larger than 100 kilometers across, and possibly trillions of smaller ones. Pluto, it turned out, was not a lonely sentinel at the edge of the void. It was simply the largest known member of an entire population of icy debris left over from the formation of the solar system roughly 4.5 billion years ago. This realization was one of the reasons the International Astronomical Union reclassified Pluto as a dwarf planet in 2006. Pluto did not change. Our understanding of its neighborhood did. Other large Kuiper Belt objects were discovered, some of them rivaling Pluto in size. Eris, discovered in 2005, turned out to be more massive than Pluto, which raised the obvious question. If Pluto is a planet, why not Eris? Rather than adding planets every time a large Kuiper Belt object was found, astronomers redefined the category. Pluto was demoted, or more accurately, reclassified to reflect the reality that it is one member of a vast population, not a solitary world at the edge of the map. For many people, the Kuiper Belt is where the updated mental map ends. The planets fill the interior. The Kuiper Belt forms a natural border at about 50 astronomical units. And beyond that, interstellar space. The void. Nothing. It is a clean, satisfying picture, and it is almost entirely wrong, because there is a category of object in the solar system that flatly refuses to fit this model, and these objects have been visible to human beings for thousands of years, long before anyone knew what a planet was or where Neptune orbited. Comets. Comets are among the oldest astronomical phenomena recorded by human civilizations. The ancient Chinese tracked them carefully. The Babylonians noted their appearances. The Greeks debated whether they were atmospheric phenomena or celestial bodies. For most of human history, comets were considered omens, signs of impending disaster or divine displeasure, precisely because they were unpredictable. Unlike the planets, which move across the sky in regular, repeating patterns, comets appear without warning, hang in the sky for days or weeks with their spectacular glowing tails, and then vanish back into whatever darkness produced them. We now understand comets as small, icy bodies, typically a few kilometers across, composed of frozen water, carbon dioxide, methane, ammonia, and dust. They are sometimes described as dirty snowballs, though the reality is more complex than that phrase suggests. When a comet's orbit carries it close enough to the sun, the solar radiation heats its surface. Frozen material vaporizes, producing a cloud of gas and dust around the comet called a coma. The solar wind and radiation pressure push this material outward, forming the long, luminous tail that makes comets so spectacular. A comet far from the sun is a dark, cold, inert lump of ice and rock. It only becomes visually dramatic when it approaches the sun and begins to shed its material. Now, comets come in two broad categories, and the distinction between them is the key that unlocks the entire mystery of the Oort Cloud. Short-period comets have orbital periods of less than 200 years. They return on relatively predictable schedules. Halley's Comet, perhaps the most famous comet in history, has an orbital period of roughly 75 to 79 years. It was last visible from Earth in 1986 and will return around 2061. Edmund Halley predicted its return in 1705 using Newton's laws of gravity, and when the comet appeared on schedule in 1758, it was one of the great triumphs of mathematical astronomy. Short-period comets tend to have orbits that stay relatively close to the plane of the planets. Their trajectories are geometrically consistent with originating from the Kuiper Belt, or a related structure called the scattered disk. They behave as though they are part of the same flat, disc-shaped architecture as the planets. But then there are the long-period comets, and this is where the comfortable picture breaks. Long-period comets have orbital periods exceeding 200 years. Some have periods of thousands of years. Some have periods of tens of thousands of years. Some appear to be on orbits so extraordinarily elongated that a single loop around the sun takes millions of years. They fall inward from staggering distances, swing around the sun in a tight, blazing curve, and then climb back out into the darkness, not to return for millennia or longer. Comet Hale-Bopp, which lit up the sky in 1997 and was visible to the naked eye for a record 18 months, has an orbital period of roughly 2,520 years. It will not return until approximately the year 4530, other long-period comets have orbits so extreme that their periods stretch beyond meaningful measurement. They may be making their first and only pass through the inner solar system, or their first in billions of years. Think about what this means. A comet that last visited the inner solar system around the time the Great Pyramids at Giza were being constructed will not come back until roughly the 46th century. It has been out there, somewhere in the darkness, following an orbit so elongated and so enormous that a single trip around the sun spans the entirety of recorded civilization. And here is the fact that changed everything. Long-period comets do not arrive from one direction. They do not come from the flat plane of the planets, the way short-period comets largely do. They arrive from everywhere. From above the planetary plane, from below it, from angles that bear no geometric relationship whatsoever, to the disc-shaped structure of the planets and the Kuiper Belt. If you plotted the arrival directions of every long-period comet ever observed on a globe of the sky, you would not get a band or a stripe. You would get a nearly uniform sphere. They rain inward from every direction, as though something spherical and gigantic surrounds the entire solar system, and occasionally sends frozen visitors tumbling in from any angle. This is a serious problem for anyone who thinks the solar system is a flat disk of planets and icy debris ending at about 50 astronomical units. A flat disk does not produce objects arriving from every direction. Only a sphere does. The long-period comets are telling us, plainly and repeatedly, that there is something spherical out there. Something enormous. Something we cannot see. And there is a second problem layered on top of this one, equally damning to the simple picture. Comets are fragile. Every time a comet passes close to the sun, it loses material. Solar heat vaporizes surface ice, and that vapor streams away, forming the tail. Each close approach strips away a layer of the comet's body. A typical comet nucleus, only a few kilometers wide to begin with, can survive perhaps a few hundred close passes before it either breaks apart completely or loses so much volatile material that it becomes inert. A dead husk of rock and dust, no longer able to produce a coma or tail, no longer recognizable as a comet. Scientists have estimated that a typical comet nucleus might survive somewhere between 100 and 1,000 close solar approaches, depending on its size and composition. After that, it is effectively gone, broken into fragments, or reduced to a dark, inert remnant that no longer outgasses and no longer displays the coma and tail that define what a comet is. This means that the long-period comets we observe today cannot have been cycling through the inner solar system since the solar system formed. 4.5 billion years is far too long. If these comets had been orbiting close to the sun for that entire span, they would have been destroyed eons ago. They must be recent arrivals. Something must have disturbed them from a distant, cold, stable location and sent them falling inward toward the sun for the first time, or at least for the first time in an inconceivably long while. The comets we see are not ancient travelers on repeating loops. They are new visitors, drawn from a reservoir that has been quietly holding them in frozen storage since the solar system was young. There must be a source, and that source must be far enough away that objects stored there can survive untouched for billions of years. This reasoning had been circulating among astronomers for decades. In 1932, Estonian astronomer Ernst Öpik published a paper proposing that long-period comets might originate in a vast cloud of icy objects orbiting at the outermost edge of the solar system. It was a logical, well-reasoned idea, consistent with the available evidence. But Opic was not widely known outside a small circle of specialists, and his proposal did not gain traction. The broader astronomical community moved on without giving it much attention. 18 years later, in 1950, a Dutch astronomer named Jan Oort changed everything. Oort was already a towering figure in astronomy. He had made fundamental contributions to our understanding of the structure and rotation of the Milky Way galaxy. He was not a fringe thinker or a speculator. He was one of the most rigorous and respected astronomers of his generation. And when he turned his attention to the problem of long-period comets, he approached it with the methodical precision that had defined his career. What Oort did was beautifully simple. He gathered the best available orbital data for 19 well-observed long-period comets. For each one, he calculated the original orbit, meaning the trajectory the comet was on before it entered the inner solar system, and had its path altered by gravitational encounters with the giant planets. This was a critical step. The orbits we observe for comets passing near the Sun are not their true, undisturbed orbits. Jupiter and Saturn and Neptune tug on every comet that passes through their domain, bending and twisting its trajectory. To understand where a comet actually came from, you have to rewind those gravitational perturbations and reconstruct the orbit the comet was following before the planets got their hands on it. Oort performed this calculation for each of his 19 comets. He then examined a particular orbital property, the reciprocal of the semi-major axis. The semi-major axis is half the longest dimension of an elliptical orbit. For a comet on a very elongated orbit, the semi-major axis tells you roughly how far the comet travels from the Sun at its most distant point. The reciprocal of the semi-major axis is a measure that is close to zero for very distant orbits, and increases as orbits become smaller and more tightly bound. What Oort found was a spike, a clustering. 10 of his 19 comets had original orbits whose reciprocal semi-major axes were packed into a narrow range, corresponding to aphelia most distant points of roughly 20,000 astronomical units from the Sun. They were not distributed randomly across a wide range of distances. They were concentrated, as though they had all been released from approximately the same enormous distance. Oort drew the logical conclusion. The Sun, he proposed, is surrounded by a vast spherical cloud of cometary bodies at extreme distance. The cloud is spherical because comets arrive from all directions. It is located at roughly 20,000 astronomical units or more, because that is where the original orbits cluster. The objects in it are remnants of the solar system's formation. Small icy bodies that have been sitting in cold storage for billions of years. Occasionally, a passing star drifts close enough to the outer solar system that its gravity disturbs some of these distant objects, nudging them onto new orbits that send them falling inward toward the Sun. When they arrive, we see them as long-period comets. The reasoning was elegant and airtight. The spherical distribution of arrival directions required a spherical source. The enormous orbital periods required an enormous distance. The pristine, volatile-rich composition of the comets required a cold, undisturbed reservoir, and the clustering of original orbital distances pointed to a specific location. Every piece of evidence converged on a single conclusion. Oort's 1950 paper became one of the foundational documents of modern solar system science. The structure he proposed became known as the Oort Cloud. It is worth noting that Ernst Opic had proposed essentially the same idea 18 years earlier, and some astronomers referred to the structure as the Oort Cloud in recognition of his priority. But it was Oort's detailed, quantitative analysis that gave the idea the evidentiary weight it needed to convince the community. In the decades since, the hypothesis has only gotten stronger. Better observations of long-period comets, more refined orbital calculations, and computer simulations of solar system formation have all supported and refined the basic framework Oort laid out. No one has found a competing explanation that accounts for all the observed properties of long-period comets as elegantly as the Oort Cloud hypothesis does. It remains, more than 70 years after Oort's paper, the accepted explanation for where these comets come from. Now, there is something important to sit with here. No one has ever seen the Oort Cloud. There is no photograph of it. No spacecraft has visited it. No telescope has directly imaged it as a structure. No individual object has ever been confirmed as sitting in its distant orbit inside the cloud and identified as a member. Everything we believe about the Oort Cloud comes from reasoning backward, from the objects it sends us, from the orbits those objects arrive on, and from the physics of how gravitational systems evolve over billions of years. We know it is there the same way, there is a factory somewhere producing the cars you see in the highway. You have never visited the factory. You have never seen the assembly line. But the cars keep arriving, day after day, in consistent makes and models, and their existence demands an explanation. The long-period comets keep arriving. They come from all directions. Their original orbits cluster at distances consistent with a distant spherical reservoir, and no other model explains all of these facts as cleanly as the Oort Cloud. The uncertainty does not weaken the story. It is part of the story. We are dealing with a structure so far away and so faint that it may remain beyond direct observation for decades or centuries. And yet, the evidence for its existence is strong enough that it has been a cornerstone of solar system science for more than 70 years. So, what is the Oort Cloud believed to be? In its simplest terms, it's a theoretical, inferred structure, not a glowing nebula, not a solid wall, not a visible shell that a telescope could photograph. It is a vast, sparse population of small icy bodies gravitationally bound to the sun, distributed in a roughly spherical shell at distances so great that nothing in the planetary region of the solar system offers a meaningful comparison. The objects in it are thought to be made of the same primordial material as the comets we observe: water ice, frozen carbon dioxide, methane, ammonia, carbon monoxide, and dust. They range in size from small chunks to objects potentially tens of kilometers across, and there are a staggering number of them. Estimates suggest the outer Oort cloud alone may contain on the order of 1 trillion objects larger than 1 kilometer in diameter, with the total population, including smaller bodies, running into the trillions. Despite those numbers, the Oort cloud is not crowded. The volume of space it occupies is so staggeringly vast that even 1 trillion objects spread across it produce an almost inconceivable emptiness. One estimate suggests that if you took a volume of 1,000 cubic astronomical units within the outer Oort cloud and counted everything in it larger than 1 kilometer, you would find roughly 2 objects. 2. In a cube of space, 1,000 astronomical units on a side. The distances between individual Oort cloud objects are enormous. If you were dropped into the Oort cloud in a spacecraft, You would almost certainly never encounter a single object by chance. You would float in darkness, surrounded by nothing visible, with the sun reduced to a faint star behind you, and the nearest Oort Cloud neighbor millions of miles away in any direction. The Oort Cloud is populated in theory and empty in practice. The cloud is generally described as having two main regions. The outer Oort Cloud, the region Oort originally identified, is roughly spherical. It is estimated to extend from roughly 20,000 astronomical units to as far as 100,000 astronomical units from the Sun, with some models pushing the outer boundary even farther. This is the zone that produces the long-period comets we observe. Objects in the outer cloud are so loosely bound to the Sun's gravity that even weak external forces, the gravitational tug of a passing star, the tidal pull of the Milky Way's disk, can significantly alter their orbits and send them tumbling inward. Inside the outer cloud, there is a denser, more compact region called the inner Oort Cloud, also known as the Hills Cloud, after physicist Jack Hills, who proposed its existence in 1981. The Hills Cloud is estimated to extend from roughly 2,000 to 20,000 astronomical units. Unlike the outer cloud, it is not spherical. It is thought to be more disc-like or donut-shaped, roughly aligned with the plane of the planets, though tilted and somewhat warped. The inner cloud may contain several times more mass than the outer cloud. It likely serves as a critical long-term reservoir, gradually feeding objects outward into the more exposed outer cloud over billions of years, replenishing the population that is slowly lost to stellar encounters and galactic perturbations. Together, these two regions form a structure that extends from roughly 2,000 astronomical units to perhaps 100,000 astronomical units or more. And here is what matters. The planets, the asteroid belt, the Kuiper Belt, everything that appears in a standard diagram of the solar system, all of it is contained within the innermost 50 astronomical units. The Oort Cloud begins at roughly 2,000 astronomical units. The outermost planets are not near the edge of the solar system. They are deep inside it. But none of this means anything yet. Not really. Because when I say 2,000 astronomical units, or 100,000 astronomical units, those numbers land in your brain as abstractions. Large numbers. Impressive in a vague way. You know they are big, but you do not feel them. You do not yet understand how completely they demolish the scale of the solar system you carry in your head. The gap between Neptune and the beginning of the Oort Cloud is not like the gap between Earth and Neptune. It is not even a similar category of distance. It is something so much more enormous that the word far stops meaning what you think it means. Understanding the Oort Cloud requires translating those numbers into comparisons that your brain can actually process. It requires taking the solar system you think you know, the one with the poster and the foam planets, and watching it shrink to nearly nothing inside a structure that no diagram has ever accurately shown you. And that is exactly where we're going next. So far, we have established what the Oort Cloud is believed to be: a vast, roughly spherical shell of icy bodies surrounding the solar system at distances far beyond the planets. We have described its two regions, the denser inner cloud and the sparser outer cloud, and we have noted the approximate numbers. The inner edge may begin around 2,000 astronomical units from the Sun. The outer edge may extend to 100,000 astronomical units, or even farther. Those numbers sounded large. They are large, but right now, they are just numbers. They sit in your mind the way a statistic about the national debt sits in your mind. You know it is big. You cannot feel how big. The goal right now is to change that. By the time we are done here, you will not just know that the Oort Cloud is far away. You will feel the distance in a way that restructures how you think about the solar system. Let's start with a comparison that sounds simple, but reveals something staggering. Neptune, the outermost planet, orbits at about 30 astronomical units from the Sun, 30 times the Earth-to-Sun distance. That is the farthest point in the solar system that most people's mental map includes. It is, in most people's imagination, approximately where things end. Now, the inner edge of the Oort Cloud, the closest boundary of the structure, begins at roughly 2,000 astronomical units. That is approximately 67 times farther from the Sun than Neptune is. Think about what that means. Neptune already feels unimaginably distant. It took humanity's fastest outbound spacecraft 12 years to reach it. Light from the Sun needs over 4 hours to arrive there. A radio signal traveling at the speed of light takes the same 4 hours, and the nearest fringe of the Oort Cloud is roughly 70 times farther away than that. To put this in earthly terms, if the distance from the Sun to Neptune were the length of a football field, the inner edge of the Oort Cloud would be more than a mile beyond the end zone. You would walk across the field, pass every planet in the solar system, reach Neptune at the far goal line, look up, and realize that the Oort Cloud does not even begin until you have walked a mile farther into the parking lot and out into the surrounding neighborhood. But we're just getting started. The outer Oort Cloud, the vast spherical shell from which most long-period comets are thought to originate, extends to roughly 100,000 astronomical units. That is more than 3,300 times Neptune's distance. If you drew a line from the Sun to Neptune on a piece of paper and made it 1 inch long, the line from the Sun to the outer Oort Cloud would be about 277 feet. The entire planetary solar system would be the width of your thumbnail on a football field. The Oort Cloud is not a little bit farther than the planets. It is not 10 times farther. It is not 100 times farther. It is thousands of times farther, and the difference between hundreds and thousands matters enormously here, because it is the difference between a distance your brain can stretch to accommodate and one that simply breaks the mental model. This is not like learning that the Pacific Ocean is wider than you thought, or that the Sahara Desert is larger than you imagined. Those are adjustments within a scale your mind already works with. The Oort Cloud requires you to abandon the scale entirely and build a new one. And the best way to do that is with a physical model. Imagine shrinking the Sun down to the size of a basketball. A regulation basketball is about 9.5 inches across. The Sun is roughly 864,000 miles in diameter. At this scale, everything in the solar system shrinks proportionally. The Earth becomes a tiny grain, about 2 millimeters across, smaller than a peppercorn, and it would sit about 85 feet from the basketball. That is roughly the distance from one end of a basketball court to the other. So in our model, the entire distance from the Earth to the Sun, 93 million miles of actual space, fits inside a gymnasium. Mars, at 1.5 astronomical units, would be a slightly smaller grain about 130 feet from the basketball. Jupiter, the largest planet, would be about the size of a large marble, roughly an inch across, sitting about 440 feet from the basketball, less than 1/10 of a mile. Saturn, with its rings, would be a slightly smaller marble, a bit under an inch, at about 800 feet. You could still see the basketball from Saturn's position in this model. You could wave to someone standing next to it. Neptune, at 30 astronomical units, would be a small ball about the size of a cherry, sitting roughly half a mile from the basketball. Half a mile. You could walk from the Sun to Neptune in about 10 minutes in this model. The Kuiper Belt, the band of icy objects extending to about 50 astronomical units, would end at roughly 3/4 of a mile from the basketball. That is the entire familiar solar system. Sun to Kuiper Belt. One building to one street corner. The whole thing fits inside a comfortable walk. Now extend the model to the Oort Cloud. The inner edge of the Oort Cloud, at 2,000 astronomical units, would sit roughly 32 miles from the basketball. Not 32 feet, 32 miles. You left the basketball Sun on a sidewalk in Midtown Manhattan, walked through the entire planetary system in under a mile, and now the nearest edge of the Oort Cloud is somewhere out past the far suburbs of New York City. You are standing in the city, looking outward, and the Oort Cloud has not even started yet, until you are well into New Jersey or Connecticut. And the outer edge? At 100,000 astronomical units, the outer boundary of the Oort Cloud in our basketball model sits roughly 1,600 miles from the basketball. 1,600 miles. That is roughly the straight line distance from New York City to Denver, Colorado. You placed a basketball on a sidewalk in Manhattan. The planets fit within the first half mile. The Kuiper Belt ends within 3/4 of a mile. And the Oort Cloud stretches from 32 miles out all the way to Denver. Sit with that for a moment. The model in which the Sun is a basketball you can hold in your hand produces a solar system that stretches across more than half the width of the continental United States. And everything you see in every diagram of the solar system, every planet, every moon, every ring, every asteroid, occupies less than the first mile. The other 1,600 miles are the Oort Cloud. Dark, cold, almost completely empty. Not a single feature worth labeling. No bright object to name. Just an immense volume of near vacuum, occasionally punctuated by a frozen chunk of ice and rock, so small and so dark that you could fly past it at close range and never notice it. No diagram you have ever seen comes close to representing this accurately, because it is physically impossible to draw. If you wanted to show the Oort Cloud at a scale where the planetary region was visible to the naked eye, you would need a piece of paper several miles wide. If you drew the Oort Cloud to fit on a single page, the planets would vanish. They would be a single dot of ink at the center of a blank sheet, and even that dot would be far too large. This is not a failure of illustration. It is a consequence of reality. The solar system is structured in a way that no diagram at any single scale can honestly represent. The planets and the Oort Cloud do not fit on the same map. They are separated by a gulf of scale so enormous that trying to show both at once forces you to distort one of them beyond recognition. That is the Oort Cloud's distance, and we have not even talked about what it would take to cross it. The fastest human-made object that has traveled outward from the Sun toward interstellar space is Voyager One. Launched on September 5th, 1977, it was originally designed to study Jupiter and Saturn. It flew past Jupiter in 1979 and Saturn in 1980, capturing some of the most iconic photographs in the history of space exploration. After completing those flybys, it continued outward on a trajectory that would carry it away from the Sun forever. It has been traveling for nearly 50 years. In that time, it has covered approximately 170 astronomical units. That is an extraordinary distance by any human measure. More than 15 billion miles, more than 25 billion kilometers, so far away that a radio signal from Voyager One, traveling at the speed of light, takes approximately 23.5 hours to reach Earth. In November of this year, 2026, Voyager 1 will reach a striking milestone. It will be one full light day away from Earth for the first time in history. 24 hours of light-speed travel between us and our most distant emissary. That is a poetic threshold. A full rotation of the Earth, dawn to dawn, and in all that time the signal is still crossing the gap. But in the context of the Oort Cloud, Voyager 1 has barely moved. 170 astronomical units is less than 9% of the way to the inner edge of the Oort Cloud at 2,000 astronomical units. It is less than 0.2% of the way to the outer edge. Voyager 1 has been flying outward for half a century, and it has not covered even 100th of the distance to the far side of the structure that defines the true boundary of the solar system. Voyager 1 is currently moving away from the Sun at a speed of roughly 3.6 astronomical units per year, which translates to approximately 38,000 miles per hour, or about 17 kilometers per second. That speed is gradually decreasing as the Sun's gravity, even at this distance, continues to tug on it. But even at its current velocity, the math is devastating. At 3.6 astronomical units per year, reaching the inner edge of the Oort Cloud at roughly 1,000 astronomical units, using NASA's lower boundary estimate, would take approximately 280 years from its current position. Reaching the more commonly cited inner boundary at 2,000 astronomical units would take about 500 years. Reaching the outer edge at 100,000 astronomical units would take roughly 28,000 years, and that is just to reach the far side. The total time for Voyager 1 to enter the Oort Cloud, cross through it, and emerge out the other side is estimated at approximately 30,000 years. 30,000 years. The entire span of recorded human civilization is roughly 5,000 years. Voyager would need 6 times that just to cross the Oort Cloud, and Voyager 1 will not be functioning for any of it. Both Voyager spacecraft are powered by radioisotope thermoelectric generators, devices that convert heat from the decay of plutonium-238 into electricity. These generators lose about 4 watts of output per year as the plutonium decays. NASA engineers have been carefully managing the remaining power for years now, shutting down instruments one by one, turning off heaters, prioritizing the most scientifically valuable sensors. It is a slow, deliberate process of letting go. Every year, the spacecraft can do a little less. Every year, another capability is switched off to keep the remaining ones alive a little longer. Both spacecraft are expected to go fully silent sometime in the early 2030s, when the power output drops below the minimum needed to operate any instruments or transmit data. After that, they will continue drifting outward as inert metal husks, carried by their own momentum through the interstellar medium. Dead spacecraft, no longer talking to anyone, still carrying the golden records bolted to their sides with greetings in 55 languages and music from across human cultures. They will drift for centuries in silence, then for millennia, and they will still not have reached the Oort Cloud. The probes that represent humanity's farthest reach into the cosmos will spend almost their entire journey as silent, tumbling artifacts, long outlived by every person and probably every institution that built them, still falling outward through a solar system that has no end in sight. Let me put this another way that might make the timescale more visceral. In 2012, Voyager One became the first human-made object to cross the heliopause, the boundary where the sun's solar wind gives way to the interstellar medium. That event was celebrated around the world, and rightly so, as a historic milestone. Headlines announced that Voyager had left the solar system. It had entered interstellar space. The boundary had been crossed. The implication in most of the public coverage was that Voyager was now outside, that it had departed. That it was, in some meaningful sense, gone. But here's the thing that almost no one mentions in those celebrations. Crossing the heliopause at roughly 122 astronomical units does not mean leaving the solar system. Not even close. The heliopause is the edge of the sun's atmosphere, the boundary of its magnetic and particle influence. But the solar system, defined by the sun's gravitational dominance, extends to the outer edge of the Oort Cloud at 100,000 astronomical units or more. Voyager One crossed the heliopause and entered the interstellar medium, but it is still deep inside the solar system. Gravitationally, it is still firmly bound to the sun's domain. It has passed through the sun's breath, so to speak, but it has not left the sun's house. It will not leave the sun's gravitational family for approximately 30,000 years. And that distinction matters, because it reveals how dramatically our casual use of the phrase edge of the solar system understates the reality. And Voyager 1 is fast. It is one of the fastest objects humanity has ever sent outward from the sun. There are other reference points that make the distance feel even more sobering. The New Horizons spacecraft, launched in 2006, reached Pluto in 2015 after a flight of about 9.5 years. At the time of its launch, it held the record for the fastest spacecraft ever to leave Earth, departing at a velocity of roughly 36,000 miles per hour. Even at that speed, traveling in a straight line without slowing down, New Horizons would take more than 700 years to reach the inner boundary of the Oort Cloud, and tens of thousands of years to cross it. No space agency on Earth has ever proposed a mission to the Oort Cloud, not as a serious funded engineering level mission, not even as a conceptual study with a realistic timeline. There have been discussions about interstellar precursor missions, probes that would fly to a few hundred or a few thousand astronomical units to study the interstellar medium and the outer boundary of the sun's influence. But even those concepts remain in the realm of advanced planning. The Oort Cloud itself, as a destination, is so far away that it falls outside the planning horizon of any existing space program. It is part of the solar system the way a distant mountain range is part of a country. It belongs to us in a gravitational sense, but reaching it is not something the current generation of spacecraft or the next generation or the generation after that is designed to do. This raises a question that is worth taking seriously because it gets at the heart of how science works in the dark, in the places too far away to visit and too faint to photograph. If the Oort Cloud is so far away that no probe can reach it, and so faint that no telescope can image it directly, How do scientists know anything about its internal structure? How can they claim to understand how it is shaped, how dense it is, how its objects are distributed? The answer is that they build models. Detailed, physics-based computer simulations that start with the known conditions of the early solar system and track what happens over billions of years as gravity, planetary scattering, stellar encounters, and galactic tides sculpt the orbits of small icy bodies outward into the deep cold. These simulations have become extraordinarily sophisticated, and in February of 2025, a team of researchers led by David Nesvorny at the Southwest Research Institute published a result that added a striking new detail to our picture of the inner Oort cloud. Using large-scale numerical simulations, they tracked the orbital evolution of small bodies as they were scattered outward by the giant planets into the region between roughly 1,000 and 10,000 astronomical units. What they found was unexpected. The galactic tide, the subtle gravitational pull exerted by the mass of the Milky Way's disk, does not just randomize the orbits of these objects, it organizes them. As the tide acts on objects at these intermediate distances, it raises their perihelion distances, decoupling them from the planets, and it rotates their orbital planes in a systematic way. The result, when viewed from a distance, is not a featureless disk or a uniform cloud. It is a spiral. A two-armed spiral structure roughly 15,000 astronomical units across, embedded in the inner Oort cloud like a vast pinwheel of icy debris. The spiral forms early in the solar system's history, within the first few 100 million years. And remarkably, it persists. It does not dissolve or scatter over time. Even when the researchers tested the effect of passing stars, which periodically perturbed the outer solar system, the spiral structure remained intact. It is stable. It is likely still there today. A hidden pattern in the architecture of the inner Oort cloud that no human eye has ever seen and no telescope has ever detected. The paper described the observational prospects for detecting this spiral as, in their own word, feeble. The objects in the inner Oort cloud are too small, too cold, and too far away to be seen with any existing telescope. The Vera Rubin Observatory in Chile, which began its legacy survey of space and time in June of 2026, is now scanning the entire visible sky repeatedly, cataloging moving objects and faint sources. It may eventually detect some of the closest inner Oort cloud objects, those with perihelia inside about 30 astronomical units. But detecting enough objects to map a spiral structure stretching 15,000 astronomical units across would require observational capabilities far beyond what is currently available. The spiral, for now, exists only in simulations, consistent with everything we know about solar system physics, but invisible to direct observation. It is a prediction, waiting for instruments that do not yet exist to confirm or refute it. But the fact that such a prediction can be made at all, that scientists can describe the shape of a structure 15,000 astronomical units across based on the physics of gravity and time alone, speaks to how well the underlying models work. The simulations that produce the spiral also produce comet populations and orbital distributions that match what we actually observe. The models are not speculations. They are physics, applied carefully and tested against every observable consequence we can measure. This is a remarkable situation. Scientists have modeled a structure roughly 15,000 astronomical units across, shaped by forces that operate on timescales of billions of years. composed of countless icy bodies that have never been directly observed, embedded inside a larger cloud that has also never been directly observed. And the physics is strong enough, the simulations consistent enough with the comets we do see, that this model is taken seriously by the planetary science community. We are mapping regions of our own solar system using mathematics and physics rather than light and cameras. Not because we choose to, but because the distances involved leave us no alternative. This is what makes the Oort Cloud so deeply strange as a scientific subject. It is not a distant galaxy or faraway nebula that we can at least photograph, even if we cannot visit. It is part of the solar system. It is our neighborhood, gravitationally speaking. The sun holds it. The planets helped build it. The comets it produces land in our skies. And yet it is so far away that we know its shape and structure only from inference, simulation, and the behavior of the frozen messengers it occasionally sends our way. And this brings us to an important point about the thickness of the Oort Cloud, because distance to the edge is only half the story. The Oort Cloud is not a thin shell. It is not a boundary line you cross. It is deep. Staggeringly deep. The inner edge may sit at roughly 2,000 astronomical units. The outer edge may extend to 100,000 astronomical units or more. That means the Oort Cloud itself, from inner boundary to outer boundary, spans approximately 98,000 astronomical units. For comparison, the entire planetary region of the solar system, from Mercury to Neptune, spans about 30 astronomical units. The Oort Cloud's thickness is more than 3,000 times the width of the planetary zone. If Voyager One enters the inner boundary of the Oort Cloud in roughly 300 years, it will still be inside the Oort Cloud 30,000 years later. For context, 30,000 years ago, Neanderthals had only recently disappeared from Europe. Modern humans were painting the walls of caves in what is now France and Spain. The last ice age was approaching its maximum. Massive glaciers covered most of northern Europe and North America. The English Channel did not exist as a body of water. Britain was connected to the continent by a land bridge. The world was so different from the one we know that a person transported from that era to this one would not recognize a single political border, a single language, a single building. And that is the time it takes to cross the Oort Cloud at Voyager speed. Everything that has happened in human history, every empire that rose and fell, every war that was fought, every language that evolved, every technology that was invented, every religion that was founded, all of it fits within the time Voyager would spend drifting through a single structure in our own solar system. If Voyager One had entered the Oort Cloud at the same moment that modern humans first began painting those cave walls, it would be emerging from the far side right about now. That is the depth of the Oort Cloud. It is not a wall. It is not a fence. It is not a thin membrane you pass through on your way out. It is a volume so enormous that crossing it at the speed of our fastest spacecraft would take longer than any civilization in human history has lasted. Longer than any language has survived unchanged. Longer than any building has stood. The planets live inside a pocket of relative warmth and light at the very center of this structure. Everything else, the overwhelming majority of the sun's gravitational territory, is the Oort Cloud. Dark, frozen, and deeper than the human mind naturally accommodates. But the Oort Cloud is not just distance and emptiness. It is populated. Sparsely, darkly, but populated. Trillions of objects, most of them smaller than a city, composed of ice and rock and frozen gases, orbiting the sun in paths so slow and so vast that a single orbit can take millions of years. And the objects that live there, the ones we have never seen in situ, the ones whose existence we deduce from the comets that fall inward, those objects have a story. They were not always out there in the cold. They were born much closer to the sun, in the chaotic, violent early solar system, and they were flung outward by the gravity of the giant planets into orbits so elongated that they stretched to the very limits of the sun's gravitational reach. Once there, external forces reshaped their paths, trapped them, and settled them into the vast reservoir we now call the Oort Cloud. How they got there, what disturbs them, and how they occasionally become the long-period comets that streak through our skies. That is the story of gravity, time, and the galaxy itself. And that is where we are going next. We have established what the Oort Cloud is believed to be and how far away it sits. But so far, we have been talking about it mostly as a location, a set of distances, a volume of space. Now we need to ask a different kind of question. How did all those objects get out there in the first place? The Oort Cloud is not a natural formation in the sense that a mountain range is. Mountains form where they stand, pushed up by the forces beneath them. The icy bodies of the Oort Cloud did not form at 2,000 or 50,000 or 100,000 astronomical units from the sun. They could not have. At those distances, the primordial cloud of gas and dust that gave birth to the solar system was far too thin, far too cold, and far too sparse for anything to coalesce. There was not enough material out there to build even small objects, let alone trillions of them. The Oort Cloud had to be populated from somewhere else. And the answer to where those objects came from takes us all the way back to the most violent era in the history of the solar system. Roughly 4.5 billion years ago, the solar system was young. The sun had recently ignited. The planets were still forming, or had just finished forming, from the rotating disk of gas and dust that surrounded the newborn star. And that disk contained far more material than what ended up in the planets. Alongside the growing giants, there were billions of smaller bodies. Chunks of ice and rock, ranging from pebbles to objects tens of kilometers across, orbiting the sun in the region where the giant planets were taking shape. These were the planetesimals, the building blocks of planets. Some of them were swept up by the growing worlds, adding to their mass, but many of them were not absorbed. Instead, they had close gravitational encounters with the giant planets, particularly Jupiter and Saturn, and those encounters changed everything. When a small icy body passes near a planet as massive as Jupiter, the gravitational interaction can radically alter its orbit. Jupiter is more than 300 times the mass of Earth. A planetesimal drifting past it at just the right angle and distance can be flung outward like a stone from a slingshot. Its orbit stretches from a modest loop around the sun into an enormously elongated ellipse, carrying it thousands or tens of thousands of astronomical units from the sun before it slowly curves back. Some objects were given so much energy that they escaped the solar system entirely, flung into interstellar space, lost forever, but others received just enough of a kick to be thrown into extremely distant orbits while remaining gravitationally bound to the sun. This process was not rare. It was not a subtle side effect of planet formation. It was the dominant mechanism by which the young solar system cleaned house. Jupiter and Saturn, and to a lesser extent Uranus and Neptune, acted as gravitational engines. systematically scattering enormous numbers of small icy bodies outward over the first several hundred million years of the solar system's existence. The process was chaotic and violent. Objects were flung in every direction. Some crashed into the sun. Some were absorbed by the growing planets. Some were ejected from the solar system entirely, thrown outward at speeds high enough to escape the sun's gravity and drift into interstellar space forever. And some received just enough energy to reach extreme distances while remaining tethered to the sun by the thinnest thread of gravitational attraction. Simulations of this era suggest that the number of objects scattered outward was immense, potentially tens of billions. The young solar system was awash with icy planetesimals, and the giant planets, still migrating and adjusting their orbits in the first few 100 million years, acted as gravitational threshers, separating the debris that would stay from the debris that would go. Most of the scattered material was lost to interstellar space, but a significant fraction, perhaps 10 to 20%, ended up on extremely elongated orbits that kept them bound to the sun at distances of thousands to tens of thousands of astronomical units. These are the objects that would eventually become the Oort Cloud, but being scattered into a distant orbit is not the same as settling into the Oort Cloud. This is a point that is easy to overlook and important to understand. A body flung outward by Jupiter into a highly elongated orbit will, by definition, return. Its orbit carries it far from the sun, yes, tens of thousands of astronomical units, but the orbit is an ellipse. It curves back. The object will eventually swing through the planetary region again on its return leg, where it will have another close encounter with a giant planet. That encounter might scatter it outward again, or it might eject it from the solar system entirely, or it might send it crashing into the sun or a planet. What it will not do, on its own, is settle the object into a stable, circular orbit at great distance. Without an additional force to intervene, these scattered objects would simply bounce in and out of the planetary region until they were lost. They would not accumulate into a cloud. Something external had to change their orbits while they were at their most distant, had to lift their closest approach points away from the planets, had to detach them from the gravitational ping pong that would otherwise destroy them. And that something comes from outside the solar system. The sun is not stationary. It orbits the center of the Milky Way, taking roughly 230 million years to complete a single circuit. As it moves through the galaxy, it is embedded in a vast disk of stars, gas, dust, and dark matter. That disk has mass, a great deal of it, and that mass exerts a gravitational pull on everything within and near it. The force is not dramatic. It is not the sharp, violent tug of a close planetary encounter. It is a slow, steady, pervasive influence called the galactic tide. The galactic tide is the differential gravitational force exerted by the mass of the Milky Way's disk. It works on the same principle as ocean tides on Earth, which are caused by the differential gravitational pull of the Moon across the diameter of the Earth. One side of the Earth is closer to the Moon than the other, so the Moon's gravity pulls more strongly on the near side and less strongly on the far side, creating the tidal bulge that drives the rise and fall of the oceans. The galactic tide works similarly, but on a vastly larger scale and with a vastly subtler touch. The mass of the Milky Way's disk pulls more strongly on parts of the solar system that are closer to the galactic midplane and less strongly on parts that are farther away. For the planets, this difference is utterly negligible. They orbit too close to the sun, too tightly bound by its gravity, for the galactic tide to exert any meaningful influence. A person standing on Earth feels the galactic tide with a force that is trillions of times weaker than the Earth's own gravity. It is, for all practical purposes, non-existent in the inner solar system. But for objects at tens of thousands of astronomical units from the Sun, the situation is fundamentally different. Out there, the Sun's gravity is a whisper. An object at 50,000 astronomical units is held by a gravitational thread so thin that almost any additional force matters. And the galactic tide, negligible close to the Sun, becomes the dominant external influence at these distances. Over millions of years, the galactic tide gradually changes the orbital properties of distant Oort Cloud objects. It can rotate the orientation of their orbits, tilt them relative to the galactic plane, and critically, it can change their perihelion distances. The perihelion is the closest point in an orbit to the Sun. For an object sitting in the outer Oort Cloud with a perihelion that keeps it well away from the planets, the galactic tide can slowly walk that perihelion inward, bringing the object's closest approach to the Sun gradually closer and closer, until eventually the orbit carries it into the inner solar system. At that point, the object becomes a long-period comet, visible for the first time in billions of years as it heats up and begins to shed its frozen surface material. The galactic disk tide is now understood to be the single most important mechanism for delivering Oort Cloud comets into observable orbits. Research over the past several decades has demonstrated that the distribution of arrival directions for long-period comets matches the pattern predicted by the disk tide. The comets preferentially arrive from galactic latitudes that align with the direction in which the disk tide is most effective at reducing perihelion distances. This is one of the strongest pieces of evidence that the Oort Cloud exists, and that the galactic tide is actively shaping the orbits of its inhabitants. But the galactic tide is not the only force at work. There is another perturbation mechanism that operates on a different timescale and in a different way, and its interaction with the tide turns out to be crucial. Passing stars. The Sun does not orbit the galaxy in isolation. It moves through a neighborhood populated by other stars, all following their own orbits around the galactic center. Most of the time, neighboring stars are far enough away that their gravitational influence on the Oort Cloud is negligible, but occasionally, a star passes close enough that its gravity significantly perturbs the orbits of Oort Cloud objects. A close stellar encounter, one where a star passes within a few thousand astronomical units of the Sun, can dramatically rearrange the orbits of objects in the outer Oort Cloud. It can nudge perihelion distances inward, sending objects on cometary trajectories toward the Sun. It can also scatter objects outward, pushing them closer to the edge of the Sun's gravitational influence, where they may eventually escape entirely. These encounters are not hypothetical. They have happened many times over the 4.5 billion years of the solar system's existence, and they continue to happen. We know this because astronomers have recently gained an extraordinary tool for reconstructing the history and future of stellar encounters. The European Space Agency's Gaia mission, launched in 2013, is mapping the positions, distances, and velocities of more than 1 billion stars in the Milky Way with unprecedented precision. Using Gaia data, researchers can trace the past trajectories of nearby stars and identify which ones have passed close to the solar system in the geological past, and which ones will do so in the future. The data has revealed dozens of past encounters, most of them at distances too great to significantly perturb the Oort Cloud, but a few that may have come close enough to matter. One of the most intriguing cases is the star HD 7977. A study published in the journal Scientific Reports in 2025 examined this star's trajectory and concluded that it passed close to the Sun approximately 2.5 million years ago. The closest approach distance is uncertain, with estimates ranging from as close as 2,300 astronomical units to as far as roughly 13,000 astronomical units. If the passage was at the closer end of that range, the gravitational perturbation would have been significant, potentially dislodging large numbers of Oort Cloud objects from their stable orbits and sending them inward toward the inner solar system. The researchers found that for the closest approach scenario, the probability of kilometer-sized comets striking Earth would have increased by roughly an order of magnitude compared to the normal background rate. A comet shower triggered by a passing star 2.5 million years ago. That timing places it near the boundary between the Pliocene and Pleistocene epochs, a period of significant environmental change on Earth. Whether a cometary bombardment contributed to that change remains speculative, but the dynamical modeling is sound. Stars do pass near the solar system. They do perturb the Oort Cloud, and the consequences can ripple inward across thousands of astronomical units over millions of years. What makes the interaction between galactic tides and passing stars particularly important is that they do not operate independently. Research published in the late 2000s and refined over the following decade showed that the two mechanisms work in synergy. The combined effect of stellar encounters and galactic tides on the comet injection rate is significantly larger than the sum of the two individual effects. This is because they complement each other. Passing stars scatter Oort Cloud objects into a specific region of orbital space that researchers call the tidally active zone. This is the set of orbits from which the galactic disk tide is most efficient at driving perihelion distances inward, into the observable region. A star passes through or near the Oort Cloud, scrambles a population of orbits, and deposits some of those objects into the tidally active zone. The galactic tide then takes over, slowly and steadily reducing their perihelion distances over millions of years until they become observable comets. Without the stellar encounters, the tidally active zone would gradually empty as the tide drains it of objects. Without the tide, the stellar encounters would scatter objects randomly without preferentially sending them inward. Together, they produce a steady, sustained flux of long-period comets, exactly what we observe. This is the mechanism that connects the Oort Cloud to your night sky. Every long-period comet you have ever seen or heard about is the end product of this process. An icy body formed near Jupiter or Saturn 4.5 billion years ago, scattered outward into the deep cold by a gravitational encounter with a giant planet. Trapped in a distant orbit by the combined influence of galactic tides and stellar perturbations. Stored in darkness for eons, orbiting the sun so slowly that a single revolution takes millions of years. Its temperature hovering just a few degrees above absolute zero. Its surface untouched by sunlight in any meaningful way since the solar system was young, and then, millions or billions of years later, nudged inward again by the same forces that trapped it. Its perihelion drifting closer to the sun, degree by invisible degree, over millions of years. Until one day, on one orbit, the geometry finally brings it close enough for the sun's heat to matter. The frozen surface begins to warm, ices vaporize, a coma forms, a tail extends, and a comet appears in the sky of a planet whose inhabitants had no idea it was coming. By the time it reaches the inner solar system and becomes visible, it has been traveling since before humans existed. since before complex life existed on Earth, in some cases. It is an artifact from the very earliest days of the solar system, preserved in frozen storage at the outermost reaches of the sun's gravitational influence. Delivered to our skies by the combined gravity of distant stars and the collective mass of the galaxy itself. But comets are not the only evidence we have. There are objects much closer than the outer Oort Cloud that seem to belong to the same story, and their orbits raise questions that are still not fully answered. In 2003, astronomers Michael Brown, Chad Trujillo, and David Rabinowitz discovered an object that did not fit neatly into any known category. It was designated 2003 VB12 and quickly given the name Sedna, after the Inuit goddess of the sea. Sedna is a distant, reddish, icy body roughly 1,000 kilometers across. Its orbit is extraordinary. Its closest approach to the Sun, its perihelion, is about 76 astronomical units. That is well beyond the orbit of Neptune, which sits at 30 astronomical units. And its farthest point, its aphelion, is roughly 937 astronomical units. It takes Sedna approximately 11,000 years to complete a single orbit. What makes Sedna so scientifically important is not just how far away it is, but how dynamically isolated it is. Its perihelion of 76 astronomical units places it far beyond the gravitational reach of Neptune. Neptune, orbiting at 30 astronomical units, simply cannot have placed Sedna on its current orbit through a simple scattering event, because Sedna never comes close enough for Neptune's gravity to significantly affect it. The closest approach Sedna ever makes to any planet is still tens of astronomical units beyond Neptune. There is no known planet whose gravity could be responsible. At the same time, Sedna's aphelion of roughly 937 astronomical units is far too close to the Sun for the outer Oort Cloud mechanisms we just described. Galactic tides and passing stars in the present-day galactic neighborhood operate effectively only on objects at tens of thousands of astronomical units, not hundreds. At 937 astronomical units, the galactic tide is far too weak to have significantly modified Sedna's orbit over the age of the solar system. Sedna is too far for the planets and too close for the galaxy. It sits in a dynamical no man's land, detached from every known force that could explain its current orbit. The discovery of Sedna was described as the first observation of a candidate inner Oort Cloud object. It is exactly the kind of body that the Hills Cloud, the inner region of the Oort Cloud, is predicted to contain. An object that was scattered outward by the giant planets early in the solar system's history, but was then detached from planetary influence by some additional force that raised its perihelion beyond Neptune's reach. What that force was is still debated. The leading explanation involves the Sun's birth environment. The Sun almost certainly formed in a cluster of stars, a group of hundreds or thousands of newborn stars packed together in a relatively small volume of space. In that crowded early environment, close stellar encounters would have been far more frequent and more intense than they are today. A passing star in the Sun's birth cluster, approaching within a few hundred astronomical units, could have gravitationally lifted the perihelia of scattered objects like Sedna, raising their closest approach points above Neptune's reach and trapping them on orbits that persist to this day, 4.5 billion years later. In that scenario, Sedna is not just a curiosity, it is a fossil from the Sun's childhood. Its orbit carries information about the environment the Sun was born into. a crowded stellar nursery where gravitational encounters were common, and the Oort Cloud was still being assembled from the debris the planets were throwing outward. In 2014, a second object with a Sedna-like orbit was announced. Designated 2012 VP113, it has a perihelion of roughly 80 astronomical units and an aphelion of roughly 450 astronomical units. Like Sedna, it's detached from Neptune's influence. Like Sedna, its orbit suggests a population of objects inhabiting the space between the Kuiper Belt and the outer Oort Cloud. These two objects are the only confirmed members of this population discovered so far, but simulations suggest there should be many more, potentially thousands or tens of thousands, orbiting in similar detached paths, too faint and too distant for current surveys to find. Each one is a fossil from the solar system's earliest era, its orbit carrying the gravitational fingerprint of forces that acted billions of years ago. And then there are the comets that arrive in our skies right now. In our lifetimes, direct physical messengers from the Oort Cloud that we can observe, photograph, and analyze. These are not historical relics or theoretical constructs. They are real objects, visible in real telescopes, sometimes even visible to the naked eye, and every single one of them carries information about the place it came from. In September of 2025, the Pan-STARRS Survey Telescope in Hawaii detected a new comet, designated C2025 R3 Pan-STARRS. Its orbit identified it as an Oort Cloud object, falling inward from extreme distance on a trajectory that had carried it through billions of years of cold storage before anything on Earth detected its approach. By April of 2026, the comet reached perihelion, passing within roughly half an astronomical unit of the Sun, and briefly achieved naked eye brightness, reaching approximately third magnitude. For a few weeks, it was visible without a telescope, a faint smudge in the twilight sky, glowing with a coma of vaporizing ice that had not seen sunlight since before the Earth existed. And then it was gone. It began its return journey outward, climbing back toward the distant reservoir it came from, dimming week by week as it moved away from the sun. The coma thinning, the tail fading, the comet shrinking back into the darkness that had held it for longer than any species on Earth has been alive. It will not return for potentially millions of years. The people who saw it in the spring of 2026 were witnessing a one-time event on any human timescale. A frozen relic from the solar system's formation, briefly illuminated, briefly visible, and then swallowed again by a distance so vast that the word far does not begin to describe it. Every comet like this one is evidence. Not proof in the absolute sense, but strong, converging evidence that a distant reservoir exists and that it is actively producing the objects we observe. The comet's orbit, its composition, its arrival direction, all of it is consistent with the Oort Cloud hypothesis and inconsistent with every alternative explanation that has been proposed. We see the messengers, we study their trajectories, we analyze the ice and dust they shed, and from those clues, we reconstruct the existence and properties of a structure we have never directly seen. This is worth being honest about because the uncertainty is real and it matters. A study published in March of 2026 compiled a comprehensive mass inventory of the entire solar system. When the researchers propagated the uncertainties through their calculations, they found something striking. 98% of the total uncertainty in the solar system's mass budget is attributable to a single component, the inner Oort cloud. We do not know how massive it is. We do not know how many objects it contains. We do not know its precise boundaries or its exact density profile. The outer Oort cloud is somewhat better constrained because the long-period comets it produces give us observable data to work with. But the inner Oort cloud, the Hills cloud, produces very few observable comets at present. Its objects are too tightly bound, their orbits evolving too slowly for the galactic tide to efficiently inject them into the inner solar system on the timescale of recorded observation. So we are left with a region that simulations predict should exist, that Sedna-like objects hint at, that the physics of solar system formation demands, but that we have almost no direct observational handle on. The Oort cloud, in this sense, is one of the great unfinished stories in solar system science. We know that something is out there. The comets tell us that. The orbits of Sedna and its detached cousins tell us that. The physics of planetary scattering and galactic tides tell us that. Computer simulations, tested against every observable we can measure, produce Oort clouds that look consistent with reality. But the structure itself remains hidden. It is too far away to image, too faint to detect directly, too sparse to reveal itself through any method other than the occasional icy body that tumbles inward and briefly catches the sunlight. We are studying a structure that spans potentially 100,000 astronomical units, that may contain trillions of objects, that may hold several times the mass of Earth, and that may define the true gravitational boundary of the solar system. And we are doing it almost entirely through inference, through the mathematics of orbital mechanics, through the physics of gravitational perturbation, through the chemistry of cometary ice, through sophisticated computer simulations that track billions of virtual particles over billions of virtual years, and through the patient observation of objects that take millions of years to complete a single journey from their home in the dark to the brief warmth of the sun. And yet, despite all of that absence, despite having no image and no sample and no direct measurement of any kind, the case for the Oort cloud is not weak. It is one of the most thoroughly supported inferences in planetary science. Every independent line of evidence, cometary orbits, dynamical simulations, the physics of planetary scattering, the existence of detached objects like Sedna, points to the same structure at the same distance with the same approximate properties. The convergence is what makes it compelling. Not any single measurement, but the fact that every approach to the question arrives at the same answer. That is not a guess. That is science, working exactly the way it is supposed to, in a place too far away for any other method to reach. The evidence is strong, the uncertainty is real, and the two do not contradict each other. Because the Oort cloud's significance does not rest on knowing its exact mass or mapping every object inside it. Its significance lies in what it does to our understanding of the solar system itself, what it means for the boundary we draw around our planetary neighborhood, what it means for the idea that we know where the solar system ends. That is the question we have been building towards since the beginning, and it is where we are going next. We have traveled a long way tonight. We started with the solar system you learned in school, the comfortable map that fits on a poster. We broke that map by introducing the Oort cloud, a vast inferred shell of icy bodies that no telescope has ever photographed and no spacecraft has ever reached. We translated its distance into terms that exposed just how far it sits from the planets. we follow the story of how its objects were scattered outward by the giant planets and trapped in distant orbits by galactic tides and passing stars. We learned that objects like Sedna sit in the gravitational gap between the planets and the outer cloud, fossils from the sun's earliest days. And we saw that the evidence, while indirect, is strong enough that the Oort Cloud's existence is accepted as a cornerstone of modern solar system science. Now we need to confront the final question, the one that everything has been building toward. What does the Oort Cloud actually mean for the solar system? Not as a scientific curiosity, not as a trivia fact about how far away some icy debris might be, but as a redefinition of the thing itself. Because the Oort Cloud does not merely extend the solar system, it transforms it into something that most people would not recognize as the same system they were taught about as children. Let's begin with a definition. What is the solar system? It seems like a simple question, but the answer depends entirely on what you mean by the boundary. If you define the solar system as the region containing the planets, then the solar system ends at Neptune, roughly 30 astronomical units from the Sun. That is the definition most people carry in their heads. It is the one implied by every poster, every textbook, every classroom model. The solar system is where the planets are. Beyond the planets, there is space. But there is another definition, and it is the one used by scientists. The solar system extends as far as the sun's gravitational influence dominates over the gravitational influence of other objects. In other words, the solar system is not defined by where the planets are. It is defined by where the sun's gravity rules. And those are two very different things. In celestial mechanics, there is a concept called the Hill sphere. The Hill sphere of any object is the region of space within which that object's gravity is the dominant force governing the motion of smaller bodies. Outside the Hill sphere, the gravity of some larger nearby body takes over. For example, the Earth has a Hill sphere. Within it, the Earth's gravity dominates, and objects like the Moon can orbit stably. Outside it, the Sun's gravity dominates, and objects orbit the Sun rather than the Earth. The size of a body's Hill sphere depends on its mass and on how far it is from the larger body whose gravity competes with it. The Sun has a Hill sphere too. It is defined by the Sun's mass and by the gravitational environment of the Milky Way galaxy. The Sun orbits the galactic center at a distance of roughly 26,000 light-years, embedded in a disk of stars, gas, dust, and dark matter. The combined mass of the galaxy exerts a tidal force on the Sun's domain, just as the Sun's gravity exerts a tidal force on the Hill spheres of its planets. The boundary of the Sun's Hill sphere is the distance at which the galactic tide becomes strong enough to strip objects away from solar orbit. Beyond that boundary, objects are no longer gravitationally bound to the Sun. They belong to the galaxy. They drift through interstellar space, subject to the gravity of whatever star or structure they happen to pass near, no longer part of any single solar system. Current estimates place the Sun's Hill sphere at roughly 100,000 to 200,000 astronomical units from the Sun. The exact value depends on assumptions about the local density of the galactic disk and the Sun's orbital parameters within the Milky Way, but the order of magnitude is well established. And here is the critical connection. That range corresponds almost exactly to the estimated outer boundary of the Oort Cloud. This is not a coincidence. The Oort Cloud extends to the edge of the Sun's gravitational reach. Beyond the outer Oort Cloud, the Sun no longer has the gravitational authority to hold onto objects. The comets and icy bodies at the very outermost fringe of the Oort cloud are barely bound, orbiting so slowly and so tenuously that even a modest perturbation from a passing star or the galactic tide can peel them away entirely. The solar system, defined by gravity rather than by planets, extends to the outer edge of the Oort cloud. That is the scientific consensus. NASA's own description puts it plainly. The solar system goes out to the Oort cloud, and beyond the outer edge of the Oort cloud, the gravity of other stars begins to dominate. This means that the solar system is not 30 astronomical units across. It is not 50. It is not a few hundred. It is roughly 200,000 astronomical units in diameter, extending 100,000 astronomical units in every direction from the Sun. Take a moment to appreciate what just happened. Two entirely independent lines of reasoning, one from orbital mechanics and one from observational astronomy, converge on the same boundary. The Hill sphere calculation starts from the Sun's mass and the galaxy's gravitational field, and works outward to find where the Sun's authority ends. The Oort cloud hypothesis starts from the orbits of long-period comets, and works backward to find where they originate. One is a calculation about gravity. The other is an inference from icy visitors that fall out of the sky. And they arrive at the same number, the same distance, the same boundary. The edge of the Sun's gravitational dominion and the outer shell of the Oort cloud are the same place. The solar system does not end, and then the Oort cloud begins somewhere beyond it. The Oort cloud is how the solar system ends. It is the structure that fills the Sun's gravitational territory all the way to its outermost limit. It is not an appendix to the solar system. It is the solar system's true shape. Now let's translate that into a unit that might carry more emotional weight. 100,000 astronomical units is approximately 1.6 light years. A light year is the distance that light, the fastest thing in the universe, travels in 1 year. Light moves at roughly 186,000 miles per second. In 1 year, it covers about 5.88 trillion miles. The outer edge of the Oort cloud sits approximately 1.6 light years from the Sun. That means the solar system, measured from one side of the Oort cloud through the Sun to the other side, is roughly 3.2 light years across. 3 light years. The solar system you were taught fills a poster. The real solar system is 3 light years wide. Now consider the nearest star system beyond our own. Alpha Centauri, a triple star system in the southern sky, sits approximately 4.4 light years from the Sun. That is about 276,000 astronomical units. The outer Oort cloud, at 100,000 astronomical units, extends roughly 36% of the way to Alpha Centauri. More than a third of the distance to the nearest star is still inside the solar system. Think about what this means for interstellar travel, even in the most abstract sense. If you launched a spacecraft toward Alpha Centauri and it traveled in a perfectly straight line, it would spend the first third of its journey still within the gravitational domain of the Sun, still technically inside the solar system, still passing through the sparse, dark, frozen outskirts of the Oort cloud. The spacecraft would not truly leave home until it was already more than a light year from the Sun. For the first several thousand years of the trip, at any plausible speed, it would be crossing territory that belongs to our star. Let that settle for a moment. The nearest star is 4.4 light years away. The solar system itself is more than 3 light-years across. The gap between our solar system's outer boundary and Alpha Centauri's gravitational domain is approximately 1 light-year, maybe slightly more. That is a genuine gap, a stretch of truly interstellar space where neither star's gravity dominates. But it is a surprisingly narrow gap compared to the size of the systems themselves. We think of stars as isolated points separated by vast emptiness, and they are, at the level of their luminous bodies. The Sun and Alpha Centauri are separated by roughly 30 million solar diameters, but at the level of their gravitational territories, at the level of their Oort clouds, they are much closer neighbors than we imagine. Their outermost possessions may drift within a light year of each other. The fence between the 2 yards is far thinner than either yard is wide. The solar systems of neighboring stars may not be separated by the vast distances we imagine. Their Oort clouds may almost overlap. The outermost, most loosely bound objects orbiting the Sun and the outermost objects orbiting Alpha Centauri may drift through a shared twilight zone where neither star's gravity holds firmly and objects can, over billions of years, transfer from one system to the other. This is not pure speculation. Simulations of Oort cloud dynamics have shown that objects at the very edge of the Sun's Hill sphere can be captured from passing stars or lost to them. The exchange is slow, measured in millions of years, but it is real. The Oort cloud is not a sealed container. It is a porous boundary, leaking objects into interstellar space and occasionally capturing objects that originated around other stars. Some of the icy bodies currently orbiting in our Oort cloud may not have formed in our solar system at all. They may be immigrants gravitationally captured from the Sun's sibling stars in the birth cluster billions of years ago, or from passing field stars encountered during the Sun's long orbit around the galaxy. The boundary of the solar system at the Oort cloud scale is not a wall. It is a gradient, a region where belonging becomes ambiguous, where the Sun's gravity fades until it is barely distinguishable from the gravity of the galaxy at large, and where objects can drift from one star's territory to another without ever accelerating, without ever doing anything dramatic, simply by being in the right place when a slight gravitational nudge shifts the balance of forces around them. Now let us place the planets inside this picture, because this is where the familiar image of the solar system finally, completely, irreversibly breaks. The planets orbit between roughly 0.4 astronomical units for Mercury and 30 astronomical units for Neptune. That is the span of the entire planetary zone, 30 astronomical units out of 100,000. In a solar system that extends to 100,000 astronomical units, the planets occupy the innermost 0.03% of the radial distance. Not 3%, not 1/3%, 0.03%. That number is so small that it resists comprehension. Consider what it means in practical terms. Everything you have ever seen in every photograph taken by every space mission in the history of a spaceflight exists within that 0.03%. Every image of Jupiter's storms, every picture of Saturn's rings, every panorama from the surface of Mars, every view of Earth from orbit, every crater on the moon, every close-up of a comet nucleus, every map of every world we have ever visited, all of it. The entirety of human space exploration, from the first satellite in 1957 to the most advanced deep space probe operating today, has taken place within a volume of space that constitutes less than 1,000th of the solar system's true radial extent. We've explored the solar system the way a person might explore a continent by walking across the lobby of the airport. We've seen a fraction so small that rounding it to 0 would not meaningfully change the number. If the solar system were a novel of 1,000 pages, the planets would fill a single paragraph on the first page. The Kuiper Belt would end before the bottom of that page, and the Oort Cloud would fill the remaining 999 pages. Page after page after page of cold, dark, nearly empty space, punctuated only occasionally by the presence of a frozen object too small and too faint to see without instruments that do not yet exist. The novel would stretch from chapter 1 all the way to the back cover, and every page after the first would tell the same quiet story. Darkness, cold, silence, distance, the occasional icy body orbiting so slowly that its motion would be imperceptible across the span of an entire human civilization. And the entire drama of planetary science, everything we have explored and mapped and photographed and celebrated, every mission, every discovery, every photograph that ever made a person catch their breath, would be contained in those first few sentences of the first paragraph on the first page. This is what the Oort Cloud does to the solar system. It does not add a footnote. It does not extend the story by a chapter. It reveals that the story we thought we knew was only the opening line of something enormously larger, and the rest of the book is written in a language we can barely read. In ink we cannot see. On pages we have never turned. The implications of this are worth sitting with, because they go beyond astronomy. They touch something about how we understand our place in the cosmos. Most people, when they think about the solar system, picture a small, comprehensible space, the sun and its family of planets, a neighborhood, something that fits in the mind, something we have explored, at least in outline. We have sent probes to every planet. We have landed on Mars, on the Moon, on an asteroid, on a comet, on the surface of Titan. We have photographed Pluto up close. We have left the heliosphere. There is a sense, not entirely wrong, that we have surveyed our home, that we know in broad strokes what the solar system looks like and what it contains. We have even named most of its significant objects. We have catalogues, databases, orbital parameters, surface maps. We have a proprietary feeling about it. This is our system. We know it. The Oort Cloud dismantles that sense of completion entirely. It says that we have surveyed roughly 1,000th of our home, that the part we have explored, impressive and hard-won as it is, represents the bright, warm, central lobby of a structure that extends outward for light years in every direction. A structure we cannot reach with any spacecraft we have ever built. A structure we cannot see with any telescope ever pointed at the sky. A structure we cannot directly study by any method available to our civilization. A structure that may contain more discrete objects than every star in the Milky Way. A structure that defines the true gravitational boundary of the Sun's family, and that makes the planetary region look less like a solar system and more like a small, heated room inside an unimaginably large, dark, cold building that has no lights and no windows. We live in that room. We have mapped every corner of it. We have sent robots to inspect its walls and its furniture. We know its dimensions and its contents with remarkable precision. But the building around us extends so far in every direction that we have never seen its outer walls. We have only inferred that they exist by watching the occasional visitor that drifts in from the hallways beyond, covered in frost, carrying the chemical fingerprints of the construction material that lines those distant corridors. The Oort Cloud is not terrifying because it is dramatic. There are no explosions out there, no violent collisions, no storms, no eruptions, no immediate threats to anything we care about. The objects in the Oort Cloud drift in near-perfect silence, orbiting so slowly that their motion would be imperceptible across 100 human lifetimes. Nothing happens there, from a human perspective. It is the most uneventful place in the solar system. The most boring, in the most literal sense. Nothing to see, nothing to hear, nothing changing in any way that a human lifespan could measure. And that is exactly what makes it so disorienting. The most uneventful place in the solar system is also, by an overwhelming margin, the largest place in the solar system. Most of the sun's gravitational territory is quiet, dark, frozen, and empty. The planets, with all their noise and colour and activity and complexity, are the exception. They are the anomaly, the statistical outlier. A tiny, improbable pocket of warmth and light and chemistry and motion at the centre of something overwhelmingly cold and still. We live in the exception. We always have. And the Oort Cloud is the rule. We tend to think of the darkness between the stars as the void, as the emptiness that separates interesting places. But the Oort Cloud blurs that distinction in a way that is deeply unsettling once you grasp it. Because the Oort Cloud is not between the stars. It is part of the solar system. It is inside our home. The darkness that fills more than 99.9% of the solar system's volume is not the void of interstellar space. It is us. It is ours. It belongs gravitationally to the sun, bound by the same force that holds the Earth in its orbit and keeps the moon circling overhead. The Oort Cloud is the solar system, in the same way that the most distant suburb of a city is still part of the city, even if the people in the center never visit it and barely know it exists. And there is something profoundly humbling about realizing that the place you live, the solar system you call home, is mostly darkness. Not metaphorically, not poetically, physically, measurably. The overwhelming majority of the sun's gravitational territory contains almost nothing. No light worth mentioning, no warmth, no weather, no geology, no chemistry of any complexity. Just frozen objects drifting in the dark, separated by distances so vast that they might as well be alone in the universe. The solar system, for nearly all of its volume, is indistinguishable from the interstellar void. The only region where it looks like anything special is the tiny, warm center where the planets happen to be. Where we happen to be. And we will not visit it. Not in our lifetimes, probably not in our children's lifetimes, not in our grandchildren's. No existing technology, no planned mission, no propulsion system on any drawing board anywhere in the world is designed to reach the Oort Cloud. It is not on any space agency's roadmap. It is not on any billionaire's aspiration list. It is not even in the category of things that futurists discuss when they talk about what humanity might achieve in the next century. The Oort Cloud is too far. Not too far the way Mars is too far, where the challenge is hard but conceivable. Too far in the way that requires a fundamentally different relationship between our species and distance. A relationship we do not have and may not develop for centuries. Voyager One, our farthest emissary, will go silent in a few years, its power source exhausted after nearly half a century of flight. It will continue drifting outward as a dead, tumbling artifact, carrying the golden record on its side, moving through interstellar space that is still inside the solar system. It will reach the inner edge of the Oort Cloud in roughly 3 centuries. It will not exit the far side for approximately 30,000 years, and it will make that entire crossing in silence, transmitting nothing, recording nothing, observed by no one. A relic from an era whose languages and nations and technologies will be unrecognizable by the time it finally, quietly, leaves the sun's gravitational family behind. The solar system we carry in our imaginations is a bright, compact, well-mapped neighborhood. A sun, some planets, a few belts of debris, and then the stars. The real solar system is something else entirely. It is a gravitational territory spanning light years, a sphere of influence so vast that the planets are barely a speck at its center. A realm dominated not by the warmth of the sun or the glow of the planets, but by the cold, the dark, the slow, and the unseen. The Oort Cloud is not a feature of the solar system. It is the solar system. The planets are just the part we happen to live in. When you look at a diagram of the solar system tonight, the kind with the sun on the left and the planets arranged neatly in a line, remember what it is not showing you. It is not showing you the 2,000 astronomical units between the Kuiper Belt and the beginning of the inner Oort Cloud. It is not showing you the Hills Cloud, with its possible spiral arms stretching 15,000 astronomical units across. It is not showing you the vast spherical shell of the outer Oort Cloud, reaching 100,000 astronomical units into the darkness. It is not showing you the trillions of icy objects drifting in orbit so slow they take longer than human civilization to complete. It is not showing you the boundary where the sun's gravity finally gives way to the gravity of other stars. It is showing you less than 1,000th of the truth. And the other 999 thousandths are the Oort Cloud. Dark, cold, almost empty, and almost entirely beyond our ability to explore. The planets are not the solar system. They never were. They are the bright, warm, inner fraction of a structure so large that it reaches a third of the way to the nearest star. A structure built from the debris of planet formation, sculpted by the gravity of the galaxy, populated by trillions of frozen objects we have never seen, and maintained by forces that operate on timescales longer than our species has existed. A structure that surrounds us on every side, in every direction, stretching outward through darkness and cold for distances that dwarf anything we have ever crossed, or measured, or photographed. We live at its center. We always have. And until tonight, most of us never knew it was there. The Oort Cloud does not end the solar system. It reveals the solar system. It shows us that the place we call home is not the small, neat, knowable neighborhood we imagined. It is something vastly larger, mostly invisible, and almost entirely unexplored. We live at the center of a gravitational domain that stretches for light years, and we have mapped a speck of it. The rest waits in the dark, patient, silent, frozen, cold beyond comprehension, and far, far larger than any diagram will ever show you. That is the true distance to the Oort Cloud. And now you understand why it breaks your brain. Not because the numbers are large, though they are. Not because the travel times are absurd, though they are that too. It breaks your brain because it forces you to accept that the solar system you thought you knew, the one with the poster and the planets and the neat little boundary at Neptune, was never the solar system at all. It was just the beginning. A single bright paragraph in a book of 1,000 dark pages that we have only barely begun to read. The next time you look up at the night sky, remember this. Everything you can see, every star, every planet, every point of light, exist inside a sphere of gravitational influence that extends far beyond what your eyes will ever show you. The sun holds its family not just across the orbits of the planets, but across light years of cold, dark space, all the way to the fading edge of its gravitational reach, where the frozen ghosts of the solar system's earliest days drift in orbits that will not complete for millions of years. The Oort Cloud is out there, right now, surrounding everything you know, too far to visit, too faint to see, too vast to map, and far, far too large to fit on any diagram you have ever been shown. We have spent tonight expanding the solar system beyond what most people ever consider. We start with 8 planets and a poster. We end with a gravitational territory 3 light years wide, defined not by light or warmth, but by the quiet, persistent pull of a star on the frozen remnants of its own creation. The planets are not the solar system. They are the exception within it. The bright anomaly. The small, warm place where interesting things happen to gather. Everything else, the vast, dark, silent, frozen majority, is the Oort Cloud, and we are only beginning to understand it. Somewhere tonight, a child is building a model of the solar system. Styrofoam balls painted in bright colours, Jupiter orange, Saturn yellow with a cardboard ring, Earth blue and green. They are hanging it from the ceiling by fishing line, proud of what they have made, believing they have captured the solar system in miniature. And in a sense, they have. The planets are real. The colours are close enough. The order is right. But that model, charming and earnest as it is, represents less than 1,000th of the real thing. The other 999 thousandths are invisible, too far away and too dark to paint, stretching outward from the child's bedroom in every direction for distances that would take light itself more than a year to cross. The model is not wrong. It is just the opening sentence of a much longer story. A story written in ice and silence and gravity on pages so dark and so distant that we have only just begun to know they exist. The planets are not the solar system. They are only where it begins. Good night,